Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at eigenvalues and eigenvectors. So remember that a matrix A confers a linear transformation on a vector X. When you multiply a matrix by a vector, you just transform the vector. You might rotate it, dilate it, reflect it, whatever. You just do some transformations to that vector. Now it turns out for any matrix A, there is a subset of vectors, some vectors are mapped by that transformation to a scalar multiple of themselves. These are called eigenvectors. So an eigenvector is a vector of a matrix, so that when you apply the matrix to the vector, all you do is stretch it. You don't rotate it or anything. You just stretch it. So mathematically, it satisfies the equation A times X equals lambda times X. When you multiply a matrix by a vector, you simply get a scalar multiple of that vector. Here, this lambda is called the eigenvalue. It's just a scalar, it's just a number, and this is called the eigenvector. Now, eigenvalues and eigenvectors are very important in solving equations in many different things, but one application that is used every single day is actually Google. Its PageRank algorithm that made them so much money, that made it such a good search engine, actually is based on eigenvalues and eigenvectors. That's how their PageRank algorithm works. They rank pages and show you the top ranked page at the top. That's why they're able to find good results. We won't be going into that much depth. We'll just be looking at how we find eigenvalues and eigenvectors. So to find the eigenvalues of a matrix, you solve this equation: determinant of A minus lambda I equals 0. Let's look at an example. So if I want to find the eigenvalues of this matrix here, A, I need to first write A minus lambda I. All that means, A minus lambda I, is you take the matrix that we originally had, which was A, and you subtract lambda from each of the elements on the leading diagonal. Because, of course, lambda times the matrix I, because lambda is just a scalar, is just this matrix here. So subtracting this matrix from A, we just subtract lambda from each of the elements on the leading diagonal. So now what we have to do is we have to calculate the determinant of this matrix A minus lambda I. So we know that the determinant is AD minus BC. So it is 3 minus lambda AD minus BC. So to find the eigenvalues, we need to find the roots of this polynomial. It's a polynomial called the characteristic equation. So if I solve it equal to 0, that's how you find eigenvalues. You find the values of lambda, such determinant of A minus lambda I is 0. Let's go ahead and do this. I'm going to expand these brackets here using FOIL. So if I were to expand this, I get lambda squared minus 2 lambda minus 3 minus 12. Collecting like terms, I simply get lambda squared minus 2 lambda minus 15 equals 0. So we can just solve this quadratic through factorization. The two numbers that multiply to negative 15 and add to negative 2 are negative 5 and positive 3. So the two solutions to this equation are 5 and negative 3. So these are the two eigenvalues of our matrix here. So how are we going to use these to find the eigenvectors? Let's find out. So now we're going to use the eigenvalues I found on the previous slide to find the eigenvectors. So remember that we're looking for vectors x such that AX equals lambda x. Now because A is a 2 by 2 matrix, this will have to be a 2 by 1 vector. So we're going to start with our matrix A, and we're going to let the vector be x1, x2. You can call them x and y if you want, doesn't matter. So I want that to equal lambda, which is 5, times x1, x2. All right, let's go ahead and do this. So if I go across by down, what I get is that 3 lots of x1 plus 6 lots of x2 is equal to 5 lots of x1. So what I'm going to do now is subtract 3 from x1 from both sides. I get 6 lots of x2 equals 2 lots of x1, or equivalently 3 times x2 is equal to x1. So when you're finding the eigenvectors, you usually only need to look at first row times first column, and that's enough. Now the reason is that there are actually infinitely many values of x1 and x2. We only need one of them. So here I'm just going to pick x2 equals 1, x1 equals 3. So this vector 3, 1 is an eigenvector. The reason that there are infinitely many such eigenvectors is any scalar multiple of this will also be an eigenvector. 6, 2, 9, 3, 12, 4, negative 6, negative 2. All of those will be eigenvectors. So if you're asked to write an eigenvector, we usually just choose the one that has the lowest possible whole numbers, sort of like simplifying a fraction, but it doesn't matter too much. Now, if we were to use this second part, 2x1 minus x2 equals 5x2, we'd get exactly the same relationship. So that's why we only usually need to look at the first row by first column. All right, let's now look at the eigenvector associated with the eigenvalue negative 3. So again, we will multiply first row by first column. We get 3x1 plus 6x2 is equal to negative 3x1. So row 1 by column 1 gives entry in row 1, column 1. So if I subtract 3x1 from both sides, I get 6x2 equals negative 6x1, or in other words, x2 equals the negative of x1. So this just tells us that our vector will be an eigenvector as long as whatever the first entry is, the second entry is just the negative of that. Again, any scalar multiple of this will also be an eigenvector. We just try and choose the vector with the lowest possible whole numbers. So this is an eigenvector. If you multiply this by this, you just get 5 times the vector, 15, 5. If you multiply A by this vector here, you just get negative 3, positive 3. You get negative 3 times this vector. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.